So the sea ice outlook was a reaction to the unexpected and dramatic decline in Arctic sea ice cover in September of 2007. Scientists have been predicting declining sea ice for years, but I don't think very many of them expected the sort of falling off a cliff experience of how steeply it declined in that particular year. So that fall, reacting to that, sea scientists, particularly under the umbrella of SEARCH, the Study of Environmental Arctic Change, organized the Sea Ice Outlook, SIO, with the idea that any group or individual could contribute their prediction for the extent of sea ice covering the Arctic Ocean in September each year. That is a specific number of square kilometers, and we would find the answer out in real time. The predictions, the SIO contributions, were to be made at the end or at the beginning of June, beginning of July, and beginning of August each year, and always looking toward the September mean extent. In 2004, the Sea Ice Prediction Network, SIPN, inherited and expanded the Sea Ice Outlook. And it's been highly successful with almost 600 predictions contributed over the past 8 years. So there have been a number of short and long papers. Two of the most detailed were one in the Geophysical Research Letters in 2014 that studied the outlook through 2013. And then more recently, the paper I just mentioned, 400 Predictions, which was published this summer in Polar Geography, and that covered the sea ice outlook through 2015. What I'm going to show you today is one more year of data because since that paper this summer, we had the fall 2016 results. And the first graph here just shows the progress of the sea ice outlook from 2008 to 2016, from about 39 contributions for all 3 months combined in 2008 up to more than 100 the last 2 years, in each of the last 2 years. And the colors here are very broad categories for the type of methods used, which might be statistical, either ice-ocean or coupled ice-ocean atmosphere modeling, some mixture of methods, and a catch-all category called heuristic, which might include just somebody's trend extrapolation, or it might be a poll of experts or non-experts. It's sort of everything else. One thing you can see with this is the increasing fraction that are made up of sophisticated coupled models. So how did we do? In this graphic, you see the red line, the jagged red line, is the observed September mean sea ice extent for these years. And starting in 2008, I've added blue squares that are the median July SIO contribution for all methods combined. And from a distant perspective, the SIO contributions as an ensemble are doing reasonably well in that they're all predicting fairly low ice extents. But if you look at them more closely, they're not tracking the observed extent very well in terms of year-to-year variations. The curve there is just a simple quadratic regression that seems to summarize the overall trend reasonably well. It doesn't, of course, give any guidance about the year-to-year changes. This graph follows the same convention. So the red line and the blue squares mean the same thing they did in the last graph, but it focuses in on just the years where the sea ice outlook has been operating from 2008 to 2016. And once again, the red line is the observed September ice extent, and the blue squares are the median July SIO prediction. So the dashed lines are the prediction errors each year. And you can see that some years the median SIO contribution is pretty close to the real value, and some years it's nowhere near. The shaded gray bands are the middle 50% of the sea ice outlook predictions. That it's the interquartile range, and you can see that in some years like 2012 or 2013, the observed ice extent is well outside the quartiles of the sea ice outlook predictions. In some years, it was higher or lower than any of the individual predictions that we received. Some years, like 2011, you can see that the median prediction was almost exactly right. This overall pattern is what we describe as sea ice prediction having easy and difficult years. There's some years where, on average, most of the methods, most of the predictions are fairly close, and there's some years in which almost none of them are anywhere near. And that's a fairly robust finding across different data sets, different types of methods, and different ways of quantifying the fit. One thing that we notice is that in years when the sea ice extent, the observed ice extent, is quite a bit different from what it was the year before, the predictions tend to be bad. So what you've got here is a scatter plot where the horizontal axis, the x-axis, is the observed change from the previous year. So 2013 on the far right was much higher than 2012. So it's got a very large observed change, almost 2 million square kilometers. And so the horizontal axis is how much did the actual ice change from the year before. The vertical axis is how far off was the median SIO prediction. And what you can see is that when the sea ice changed a lot from the year before, the predictions are fairly terrible. And when the sea ice did not change very much from the year before, the predictions, median prediction comes in reasonably close. And the fit's quite good. Overall, the change from the previous year explains about 86% of the variance in sea ice prediction errors. So that leads to the suggestion or the question: is the sea ice outlook doing any better than random chance in predicting the observed extent each year? So table one, and this is an update version of something that appears in our paper this summer, compares the SIO July median or errors from the SIO July median with errors you would get if you just guessed that this year's sea ice would be a linear extrapolation from the previous, from the trend up to that point, or if you just guessed that it would be a quadratic, a slightly downward steepening curve extrapolation from previous years, or if you just guessed persistence. This was Walt Meyer's idea that what if you just guessed that this year will be the same as last year? How right or how wrong would you be? So we have two columns there. One is the root mean squared error, and the other is the median absolute error. In both cases, it's a measure of the distance between the sea ice outlook, the median sea ice outlook, and the actual observed extent. And just scanning the columns, basically the sea ice outlook July median does better than linear extrapolation, does better than quadratic extrapolation, does better than persistence by either the RMSE or the median absolute error criteria. So it is not, you couldn't simply guess what it will be the same as it was last year and do equally well. The improvement is not nearly as dramatic as most people studying sea ice would like it to be. But nevertheless, it does appear that the SIO is doing better than any of these very naive null hypotheses. Table 2, likewise an update from our paper this summer, and that was in polar geography, is a more elaborate analysis in which we basically do a median regression of the median absolute prediction error as a function of year, of month. This is the month terms there to test whether the July or August predictions significantly improve on those made in June, and the type of method used, whether heuristic, modeling, statistical, etc. And I've color coded these so that the colors indicate statistically significant differences. And if it's a blue difference, then it's bad. That is, the prediction error under that condition is higher than the base category. A red value or a negative prediction error means that the predictions are better, they're more accurate than the base category. The first set of things under year, the blue and red patterns just highlight easy and difficult years. The 2011 was the predictions were very close to accurate. In other years, generally, you see 4 other years or 3 other years where the predictions are significantly worse than average. Those are difficult to predict. Years of 2008, 2009, 2012, and 2013. They stood out on the graph as well, and also in this multivariate analysis. As far as month, I think we would all like to have seen that the predictions get better comparing July with June and then August with June, but statistically they do not. There's not a significant improvement as the summer goes on. The predictions in August are slightly lower, prediction errors rather, are slightly lower, that is negative coefficients, but these are not quite statistically significant. Finally, the last set of coefficients there is testing whether certain types of analysis are better than others. And across several of these models, the statistical predictions performed better than heuristic, which is the base category here. And in some conditions, the ice-ocean atmosphere coupled models also perform better. Again, red means the effect is statistically significant and it's good, meaning the median absolute error under that condition is lower than the base category. So statistical predictions and at least some of the time ice-ocean atmosphere do better than the heuristic category. Uh, Otherwise, the differences are not striking. And really, the magnitude of those effects from different method types are uh, often smaller than the magnitude of year effects. So year effects are large. And the year effects, more or less, as we'll see, reflect the classical distinction between climate and weather. Before I go to that, I'll take a look at just what 1 year of sea ice outlook predictions look like. This is the most recent year, 2016. And each little trio of same color box plots here is the distribution of June, July, and August predictions by that particular method, starting with heuristic, then statistical, mixed, and ice ocean and ice ocean atmosphere modeling. The boxes range from first to third quartile in each distribution, and there's a line in the middle that's the median for each distribution. Gray line toward the upper part of the graph is the actual number that all these predictions were trying to guess. And you can see that the median for every type of method was below the actual observed September ice extent. And there's this year, it seems like the modeling methods on average did better than statistical. In some other years, the statistics has done better, and that there's not a clear systematic pattern to that. There's some years when statistics seems to be a better prediction strategy, some years when modeling does. So let's go back and take a look at that a little bit more closely. Uh, what happened in 2016 is that the ice extent for much of the year was on course to be a record or second lowest uh, record low level. But then, after reaching the second lowest 1 day value in early September of 2016, the ice refroze very rapidly, so that the September average was much higher than anyone would have expected from what had gone on earlier that year. And it's reflected in this graphic by the fact that the little blue square for 2016 lies pretty much exactly on the quadratic trend, but the observed ice extent, the red dot, is a bit higher than that. There was more ice on average for September than would have been expected by the trend. Basically, the predictions do fairly well when ice is more or less on its trend, and you might say that's when the ice extent is the September ice extent is dominated by climatology, and the predictions do worse when there are weather events through the middle and late summer that move it well off that trend, such as the very rapid refreezing in this September. Uh, this is a cycle plot in which each of those little squiggly lines is either the extent or the area for 1 month of the year, combining all values from 1979 through 2016. So, for example, the leftmost part of the graph are October mean ice extent and area. The dark blue line is extent, and the light greenish line is area for 1979 through 2016, with a little orange marker for 2016. And you can see that even though the September extent, the mean September extent, was only the fifth lowest in this record, for much of the year, it was the lowest. For January through June, but also October, it was the lowest. And then for November, which is the second set of squiggles from the far left, it was by far the lowest ice extent that we've ever seen. Here's one more look at how exceptional September of 2016 was after a statistically unexceptional September. We have a statistically very exceptional November. This is just a one-day extent on November 11th, and it was the lowest by a long shot of any November 11th in the satellite record, as was November as a whole. So the last slide I have is just the citations to some of the papers that describe these data and some of the related data. These are all available. Let's see, almost all. The new paper is open access, and so are most of the others, except for the GRL paper from 2014. If anybody wants to see these, you could send me an email, and I'd be happy to forward the PDF files. So that wraps up my talk. Jessica, do we have questions now, or go on to Ed's talk?
What would you like to do, Martin?
Let's have Ed give his part of the talk and then save questions for Larry and Ed till the end.
Okay, here's Ed's presentation.
Hi, this is Ed, and thanks Larry for that talk. And I'm going to talk about two things. Since Larry I guess ended mentioning how extreme November conditions have been, I wanted to show a few slides showing where we think that might be happening. And then I will discuss the results of the local sea ice forecast from this year's Sea Ice Outlook. Then I'll end up with a little plug for the end of season report that we're producing right now and will be available pretty soon. Essentially summarizing, these are sort of the two or the things going on that the current pretty extreme conditions we're seeing in terms of sea ice, very reduced sea ice, looks to have been preconditioned by the summer sea surface temperatures and upper ocean conditions. And then for the local sea ice forecast, I'll show results from the of sea ice probability, which is the probability, the regional probability of there being sea ice or not in September. And for this year, we had seven different modeling centers contribute a forecast, and we had 16 total sea ice probability forecasts, and both these numbers are all-time records. And we've been requesting these sea ice probability forecasts for the last 3 years, and it's very encouraging to see that we're having more and more submissions every year. So I wanted to show the ice concentration anomaly maps for the last few months, or every other month from May onwards. And these are anomalies with respect to the last 10 years of data. And I just want to point out how extreme November is. And you can see a really reduced sea ice, particularly in the Barents Kara seas and in the Beaufort Chukchi regions. So the sea ice edge is just a lot further north than we'd expect it at this time of the year in those regions. The Laptev, on the other hand, is pretty close to average. And if you compare the map of November with the previous maps, September, July, and May, it's you know, we don't really see much of a comparable anomalies. You know, so the September anomaly map is a lot less extreme than the November one. And so why might have these conditions developed over the last couple of months in the Arctic? And one of the clues, we believe, is in the upper ocean NSST maps. And here we go. If one looks at the July midsummer sea surface temperature anomalies in the Arctic, and let's see if I can get a pointer. So if one looks at the Barents Kara region where the pointer is and the Beaufort, we see very, very warm sea surface temperatures. And if you compare these this map with the map of the September concentration anomaly, the November concentration anomalies, we see quite a bit of correspondence. And another interesting thing is that, for example, the Laptev had close to average or even slightly cool SST anomalies in midsummer, and this is a region that is probably one of the only regions that in November has sort of climatological sea ice. And there's quite a bit of theoretical work linking summer sea surface temperatures with fall sea ice conditions. So this is evidence of this mechanism actually at play. And the other thing I wanted to mention is that we believe that these midsummer SST conditions developed from the sea ice actually in the spring. So if you look at the anomalous sea ice conditions in May, these regions, the Beaufort here and the Barents and Kara, melted back unseasonably early, and that's just given more time for the ocean to warm up throughout the summer. And just to sort of prove how extreme these conditions are, these are the average time series of the average of the monthly average SST anomaly in those regions relative to the satellite era, 79 to 2005. So for the Barents Kara, it's half a degree warmer than the previous record, and then the Beaufort Chukchi isn't quite. It's the third warmest on average, but still very warm. So we think that's basically the preconditioning of the current sea ice conditions, and seeing the timing of these mechanisms, the late spring sea ice loss and then the very high summer SSTs, we believe that there was probably some predictability of these extreme November sea ice anomalies. All right, now I'll talk a little bit about the regional sea ice outlook forecast of sea ice probability. And as I mentioned, we've been requesting these forecasts since 2014, and this is partly in recognition to stakeholder needs for forecasts that go beyond sea ice extent. Sea ice extent is just one single number, and it just integrates the whole Arctic, and it's perhaps of limited use to groups and stakeholders that are interested in particular locations. And the variable I'm showing here, which we call the sea ice probability, is just the probability that at each grid cell there's sea ice concentration above 15%. In other words, what would trigger a sea ice extent in that grid cell, and it goes from 0 to 1. So a value of 1 means there's a 100% probability of sea ice in that grid cell. And I'm showing results from the June forecast, sea ice probability, and there's 5 different models here, and the bottom right is the model mean result, and in black I'm showing the observed sea ice extent edge for September. So we're looking at how these red, the red shaded maps compare to the black contour. And for example, in June, you can see that on the Atlantic side, I'll just show for the model mean, on the Atlantic side of the Arctic, the models actually do pretty well. And on the other hand, on the sort of Pacific or the East Siberian / Alaskan side, there's quite a bit of mismatch between the observed sea ice edge contour in black and the red shading. And this was for the June forecast, and if I show you the August forecast, there isn't a huge amount of change. You can see that on the Atlantic side. Again, it's agreeing pretty well with observed values. And however, in East Siberia, where we had this tongue of sea ice in observations that almost melted out, but didn't quite, and this sea ice island remained throughout September. And there's, on the other hand, there was quite a bit of melt back here, where it went almost to 85 degrees north. That was pretty hard to predict. The models, some of the models predicted tongue of sea ice, like the NOAA model or the Naval Research Lab here. The GFDL had this tongue of sea ice, but just in the wrong location, as you can see here. And the Met Office was also very, had a large degree of uncertainty within its own forecast ensemble of how much that sea ice tongue was going to melt or not melt. And if we look at the monthly mean sea ice probability forecasts from all these models, and remember for each month we have about either 5 or 6 models submitting forecasts. So these are the averages of about 5 or 6 contributions. We can see that this sort of uncertainty actually increased from June to August. So in terms of the East Siberian sea ice tongue here. And if you look at the across model uncertainty, so if you calculate the standard deviation of all the different models that submitted their forecast, you can see two things I'll point out, and that one is that on the Atlantic side there's very little uncertainty, and actually that's kind of a good sign that the models are all forecasting pretty similar sea ice probabilities in that region, which were actually pretty close to the observed value. And you can see, on the other hand, that on the East Siberian or the Pacific side, Pacific basin side of the Arctic, East Siberia, both for Alaska, there's higher values of sigma, which means higher uncertainty across the models. Now, we're not exactly sure why that's the case, but these forecasts are very useful. And I think it's also very useful as a forecast to be able to give an estimate of uncertainty, right? So if you were a stakeholder, we'd be able to tell you whether the forecast was uncertain, but also whether the forecast is rather more certain. It's interesting that this, this region of sea ice in East Siberia, which was actually the region that froze up very fast in the second half of September that Larry mentioned, that seemed to just have been the result of fairly unpredictable kind of atmospheric synoptic noise throughout the second half of September that, months before was very, perhaps impossible to predict. Now, one of the ways we're quantifying skill in these forecasts is with the Breyer score. So the Breyer score is the squared difference between the probability, the forecast probability and the actual observation. And a score of 0 is a perfect forecast, and a score of 1 is a perfectly erroneous forecast. So 1 would be where you predict sea ice, but there's no sea ice, or vice versa. And these are the scores from 5 different submissions in August, and you can see what I was alluding to before, that most of the red values are sort of in this region of the sea ice tongue. Whereas in the Atlantic side, we're doing quite a bit better. The X labels are the Arctic mean Breyer scores, so just taking a spatial average over the Arctic basin of this field. And you can see, for example, that the best forecast for this, for the August sea ice outlook, was the Alfred Wegener Institute forecast. And you can also see that the model mean tends to do pretty well and beats all of the single submissions other than the AWI forecast. Now, if we plot these values, these Arctic mean Breyer scores for 3 months, we can see there's a bit of spread across the different forecasts. There's also a little bit of improvement between June and August, but it's very subtle. So this is similar. This, again, is similar to Larry's result for total sea ice extent, that we're not seeing too much of an improvement between June and August. And my last slide will, coming up in a few slides, will perhaps hint at why that is. Now, if we look at the model mean skill score, we see that on average it does pretty well. It beats over half the models every month. And this is common to other climate forecasting systems, right, that the model mean does fairly well. It doesn't beat all the models, but it does do fairly well, and you do see this improvement from June to August. But again, it's very subtle. And we can compare to 2015 Breyer scores. So in the red asterisks are the skill scores from last year's sea ice probability forecast, and the black asterisks are this year's. And it seems that last year we had less forecast, but it seems that there was slightly more skillful So you can see the values tend to be a little bit better, or we don't have any high values going above to 0.15 like we did this year. Now, it's, I mean, just comparing two different forecasts, or last year with this year, and we don't know exactly why, or the exact reasons why 2016 was more, seems to have been a bit less predictable in 2015. It might have been that fast freeze up at the end of the month. Another hint might be from looking at the spatial maps of comparing the 2 years, and 2015 was fairly zonal, the sea ice contour. There are some kind of indentation to that contour, but you can see that it's north of the median sea ice edge pretty much everywhere in the Arctic. Whereas 2016 here on the right, you can see that we even had some sea ice actually south of the median sea ice edge here, and a rather large sea ice island, but we had some big indentation. So it just seems like that sea ice edge was more sinuous and perhaps a little harder to predict compared to last year. And to conclude, I just want to show a plot that given to me courtesy of Frank Kauka, who's one of our collaborators in the post-season report. And he's compared how well the models did this year by splitting models that assimilate ice observations into the forecasts, and with models that do not assimilate ice observations into the forecast. So this is basically incorporating information from sea ice into the initial conditions that make the forecast. And you can, and in the orange bars here are the models that do incorporate sea ice information, and you can actually see that they're quite a bit closer to the observed value of 4.72, and compared to the grey ones, which are down here at 4.2. Now, the other interesting thing to note in this graph is that the models that do incorporate sea ice conditions do actually, if you change, the forecast as they go from June to July to August keeps getting closer and closer to the observed value. So in other ways, you're incorporating information through the summer that is having you forecast values closer to the observed September extent. Whereas the models that did not incorporate sea ice, their forecast, they do increase a little bit, but it's very little. You can say that these gray error bars are pretty much unchanged. But so that's I think a strong hint, and a direction, or it hints at the direction in which we can obtain more skillful forecasts, and it's really putting efforts into incorporating information from the sea ice as we go through the forecasting period in the summer. And so I just want to make a plug for this post-season report that will be on the Sea Ice Outlook website. And with that, I'll end my talk. Thanks for listening.
Okay, thanks very much, Ed and Larry, for giving us the latest available information. I know you've presented some of these data earlier in the fall, and it's great to have the additional information that you've developed since then. So I'll open the floor to questions. And you can ask your questions orally, or you can use the website, I believe, in the chat, and put your question in there. And please don't be shy. Okay, I'll start off with a question for Ed. In the map you showed of sea surface temperature anomalies, it was very warm water in the Beaufort Sea, but it was slightly cooler, not quite as anomalous in the Chukchi Sea. Yet the Chukchi Sea has, at least over on the Pacific side of the Arctic, is the last area to freeze over. I haven't looked at today's or the weekend's ice chart, but there's probably still open water there, or no more than 15% ice cover. So if sea surface temperature is playing a role, which I'm sure it is, what else might be going on in the Chukchi that delays freeze-up there?
That's a really good question and a very good observation. And my feeling, so there was actually a recent paper, I think it's by Mark Serres and co-authors, looking at actual freeze-up in the Beaufort Chukchi area, through the historical period and looking at the what contributes to the timing of freeze-up. And they found that summer or late summer SSTs is a factor that, there's a couple other contributors, and one of them was just the atmospheric forcing during the time of freeze up. So what's the weather doing? What was the weather doing during October? And I noticed this year there was extremely strong southerly flow in that region throughout pretty much the whole month of October. And we had some very strong cyclones that would sit up in East Siberia, and very strong southerly winds. So both dynamically and thermodynamically, I think you would just stop in any sea ice forming there. And I remember sort of staring at these maps sort of daily and just looking at the sea ice edge, and just the sea ice edge from September through October was just pretty much static. It just was not advancing at all. So I think that's one of the factors that happened in that region, where you probably had a bit less preconditioning from the SST field, but you, on the other hand, you just had this very strong atmospheric forcing that basically just was leading to the lack of sea ice there.
Okay, thank you.